Okay. Hi, everyone. So thanks very much for the introduction and thanks for attending the talk. Yeah, so this is memory bounds for the expert problem, joint work with Vaidehi Srinivas at Northwestern, Neil Shu, and Samson Joe. Okay, so yeah, what is the experts problem? So this is a problem of sequential prediction. You have a bunch of experts. They don't need to be experts. They're just people with opinions. And you have days. So on the first day, maybe you're trying to predict weather. So on the first day, the first expert might say it's going to be sunny. And the next expert might say it's going to be rainy. And the next expert might say it's sunny. The next expert might say it's sunny. And you look at all this expert advice and you want to predict, is it going to be sunny or rainy? How you do this? Well, that's where the algorithms are involved. But then you observe the actual outcome on that day. Okay. And given this outcome, it may influence how you pay attention to the different experts. But then you move on to day 2. Okay. And here are the predictions from your 4 experts again. And you might decide to pay more attention to experts that got the answer correct on the previous day, or maybe some other algorithm. But again, you're tasked with coming up with a prediction for that day, and then you see the actual outcome, and this process repeats. Okay, so you have the same set of experts on each day making predictions, and a sequence of days where you observe the predictions for that day, you make your guess, and then you see the actual outcome. Okay, so this is the experts problem. And we want to measure the performance of an algorithm for this problem. It's trying to make these predictions. And we're not going to make any distributional assumptions on the experts or outcomes. The way we're going to measure performance is by using the standard notion of regret. So the regret here, this definition, is just the number of mistakes our algorithm makes more than that of the best expert. Okay, so you have a bunch of experts, and at the end of all these days, you look at the expert that made the fewest mistakes, and you measure your algorithm's performance by looking at the number of mistakes more than that of the best expert, and you divide by the total number of days. Okay, so this is like your mistake rate on top of what the best expert's mistake rate is. Okay, so yeah, here is the same example again with these 4 experts, and you can see here in the boxes these are mistakes. So you see that on day 1, the second expert made a mistake, but the other 3 experts were correct. And maybe you went with the majority. You said that it was going to be sunny, and you were correct. And so you can see that the first expert is wrong 1 out of 4 days, and the remaining 3 experts are wrong 2 out of 4 days. And if you look at your guess, we didn't say how you form it, but if you look at the guess, you're wrong 2 out of 4 days. Okay, so you're wrong 2 days. The best expert is this first column. The best expert is wrong 1 day. So you make 1 additional mistake on top of the best expert. So the regret is 2 minus 1 divided by the number 4 of days. Okay, so you get 1/4 regret in this example. And by the way, please, stop me at any time. I'm happy to ask questions, or I'm also happy to monitor the chat box. Okay, so this is the standard notion of the experts problem and regret. And let's just set up some notation. So we have n experts who each decide on a binary outcome, 0 or 1, on each of capital T days. Okay, all of this, of course, generalizes to more outcomes and so on. And your algorithm sees the expert predictions and predicts either 0 or 1 on each day. Then the algorithm sees the outcome, which is in 0, 1, and can use this information on future days. And the cost of the algorithm is the number of incorrect predictions. And the regret, as we said, is number of mistakes we make minus m, capital M here being the number of mistakes of the best expert divided by the number t of days. Okay, so just keep in mind n experts, t days, binary outcomes. And there are many applications of the experts problem. In ensemble learning, of taking a bunch of weak learners and boosting it to a strong learner. This is AdaBoost. It's used in forecast and portfolio optimization, online convex optimization, much more broadly. Okay, so I haven't said how you predict your outcome on each day. So there are a bunch of classic algorithms for this problem. The weighted majority algorithm. Oh, sorry. Of Littlestone and Warmups from a long time ago. So here you're going to have weights for each of the experts, and so you see that. Can I annotate here? No, I guess not. Okay. Well, okay. So you see that under these 4 experts, there are these 4 weights. They're all initialized to 1, and what you're going to do is you're just going to, on a given day, you're going to go with the weighted majority. Okay, so I look at Sunny and I see that the sum of the weights is 3 for Sunny, but for Rainy the sum of the weights is 1, so I'm going to predict Sunny. And then there's some actual outcome. And I look at the experts that got the actual outcome wrong. I see the second expert said it was going to be Rainy, but actually it was Sunny. So I downweight their importance. Okay, so instead of having a weight 1 going on to the next day, the weight is now 1 minus epsilon. Okay, for some positive epsilon. And the other 3 experts got it right, so their weight remains 1. On the second day, I again take the weighted majority, and I see that Rainy, has weight in total 3 minus epsilon versus 1 for Sunny. So I predict Rainy. I get the right answer. And then, this third expert had it wrong, so I downweight their importance, and so on. So I'm maintaining a weight for each expert. Sort of the higher weight is sort of trying to indicate that the expert is more reliable or more accurate. And that's the weighted majority algorithm, classic algorithm. The guarantee for weighted majority, so this is deterministic weighted majority, is that the number, if you look inside this box, the number little m of mistakes made by the deterministic weighted majority algorithm is at most 2 plus epsilon, quantity times the number capital M of mistakes the best expert makes, plus 2 divided by epsilon times log of the number n of experts. And epsilon here is a parameter. Okay, you can choose it however you wish, but you're going to get at most at best a 2 approximation, right? You're going to make at least twice as many mistakes as the best expert. That's tight for deterministic algorithms with a simple n equals 2 example. And the proof of this is is very simple. Like it's a potential function based proof. So you look at the sum of the weights of all the experts, and it fits in this one line. It's at least the weight of the best expert, which since the best expert made at most capital M mistakes, it's at least 1 minus epsilon to the m, right? Because the weight starts at 1 and you get penalized at most capital M times. And it's also at most 1 minus epsilon over 2 to the little m times n. Why? Because all the weights start off at 1, so the sum is n. And every time you make a mistake, recall that you're going with the weighted majority. Okay, so if you make a mistake, what this means is at least half of the weight, the total weight that you currently have, gets cut down by, gets multiplied by a 1 minus epsilon factor. And so what that means is that the total weight that you have at that time gets multiplied by at most 1 minus epsilon over 2. And little m is the number of mistakes you made. And so whenever you make a mistake, this happens. Yeah, the weights can never go up. So you get these 2 inequalities. and then you just solve for your number little m of mistakes, and you get this bound. Okay. Okay, so that's the deterministic weighted majority, which is here in this top box. And in the bottom box, there's a randomized weighted majority or multiplicative weights algorithm, which bounds the expected number of mistakes made by your algorithm. Instead of getting a 2 plus epsilon approximation, you can get the expected number of mistakes by your algorithm is at most 1 plus epsilon times the number m of mistakes of the best expert plus order natural log over n over epsilon. And again, you can choose epsilon however you wish. So this is giving 1 plus epsilon, and if you set epsilon very tiny, then you have a very small additive number of additional mistakes. Okay, so let me just say where we are. This is all just background. So weighted majority algorithm downweights each expert that is incorrect on each day and selects the weighted majority as the output. It gets this bound in red in the second bullet that I said. The randomized weighted majority does better. You can think of it as you have these weights for the experts, and then you randomly sample an expert proportional to its weight, and just predict whatever that expert outputs. And by setting epsilon appropriately, the regret of this algorithm is order square root log n over t. Okay, so n experts t days, order square root log n over t. So you make the number of mistakes of the best expert plus t times this quantity, right? Remember, this is normalized by t. So it's significantly sublinear. Okay, so the issue that we looked at in this work is, well, all of these algorithms, they require omega n memory, right? You're maintaining a weight for each expert. And big data and so on, what if n is very large? What if you have a lot of experts making predictions, lots of different optimization problems, constraints could be experts and so on, n could be very large. And what if you want sublinear and n memory? Okay, what's possible? Yeah, I mean, so there's, if you want to do silly things with no memory, you can just randomly guess each day. And this might be good if the best expert makes a lot of mistakes, but in general, in that sense, if the best expert is making mistakes all the time, then maybe you're not making much more than that. But if the best expert is not making many mistakes, you have to do something, and that's not going to work. And so the question is, what are the space accuracy trade-offs for the experts problem? Okay, any questions? Okay. So yeah, so we look at this in the streaming model, which you've seen in the workshop today. And here is kind of a cute slide that my co-authors made. So here's one way of doing the streaming model. You wake up one day, you have no memory, except some note from your past self, which has at most s bits. Okay, so you made some note to yourself. And what happens in this experts problem in the streaming model? Well, then you walk through the n expert predictions for that day. And you see them one at a time, and then you make your prediction. And all the while you're using s bits of memory. Though our lower bounds actually hold more general. Actually, even if you store all the predictions on a day, for that day, and then forget it for the next day. But just think of this as a streaming algorithm that's making that's using s bits of memory on each day. You make your prediction, you see the outcome, and then you write a note to your future self, right? Using s bits s bits of space again, and you fall asleep, you forget everything, and you repeat. Okay, so this is how the streaming model works, or at least how we model it for the experts problem. Okay, so each day we stream through all the predictions, we make our guess, and then we see the actual outcome. We store a little bit of information, and we move on to the next day. Okay, so yeah, more so here is just the streaming model and different versions of it. So this sequence of t days. Oh, I see a question. Are we keeping the order of the experts fixed? Yeah. So yeah. I mean, so it doesn't actually matter. It doesn't actually matter for our algorithms. You'll see later that we're just going to sample a subset of experts on a day, and so as long as we have their IDs, that's enough. So within a day, the experts can not be ordered, but they should be labeled, right? So so the answer to that question is it doesn't have to be.
Right. Yeah, thank you. I guess my question is are they labeled? Because you don't have the memory to write down their label. So, yeah.
Well, you get like a prediction from like Bob, and the guy Bob, right?
That makes sense. That makes sense.
Okay. Yeah. So the complete sequence of t days is the data stream. I just have prediction 1, outcome 1, prediction 2, outcome 2, and and so on. And there are two notions of data stream model, that certainly not unique to this work. There's the standard arbitrary order model, which is the usual data stream model, in which case, the stream is arbitrarily ordered. So, you can think of having an adversary choosing a worst case ordering of the days. And, whatever input it wants, for the outcomes, for the predictions of the experts and the outcome on that day. And you see all the predictions of a day at once, but it can order the days however it wants. That's the arbitrary order model. And then there's the random order model, where again think of an adversary as choosing all the outcomes of the days and the corresponding predictions of the days. But then what's random is that the days are randomly ordered. Okay. So this potentially makes things easier. Namely, like if you have an expert that's pretty good on a typical day, then if you look at like a subset of contiguous days, then the expert is pretty good there too. Okay, which you might not have for the arbitrary order model. So yeah, these are standard data stream models. Okay. Okay, so how are we going to solve this problem? So a natural idea might be, can we somehow just find the best expert? If we knew who the best expert was, then we could just follow the best expert. And it's easy to see that this actually requires omega n memory. And this is pretty unfortunate for this problem. And there's a simple reduction from the set disjointness communication problem. So yeah, I mean, this is a standard communication problem, set disjointness communication problem in green here. So you have two players, Alice and Bob. Alice has a set X, which I'm just identifying with its characteristic vector in 0, 1 to the n. And Bob has a set Y, also in 0, 1 to the n. And the promise is that either of these two sets, X and Y, they are disjoint. So their intersection size is 0, or they intersect uniquely in one item. And Alice and Bob are going to talk to each other, and they're trying to minimize how much they talk to each other, but any randomized protocol for set disjointness requires omega n bits of communication to decide this answer. So you can easily embed this into our problem, even for just 2 days. Okay, so we're going to have 2 days, and the first day is going to belong to Alice. What does that mean? So you can actually copy this if you want a general number t of days, but just think of 2 days. So Alice has this set X, and it's a length n bit string, and some of those bits are 1 and some are 0, and the ones are going to indicate the experts that are correct on day 1, right? It's pretty natural. And she just creates her stream of predictions based on X. and feeds that into this streaming algorithm for the experts problem. Similarly, Bob creates a stream S prime, with the same thing, with the same, he takes his set Y, and those are the experts that are correct on day 2. Okay, so the streaming algorithm runs on day 1, and here's these are the experts that are correct, and also on day 2, these are the experts that are correct. Yeah, so Alice runs this streaming algorithm A on the stream S, passes the state to Bob, who continues the algorithm on his stream S prime. And if you could identify the best expert, well, if they intersect these 2 sets, then there's an expert that's right on both days. And if they don't intersect, there is no expert that's right on both days. So if you can find the best expert, you output this index I. And set disjointness is hard for multi-round communication. So if you have an index I, you can verify if there's actually an intersection with an additional round of communication. Anyway, just identifying this index I requires omega n communication. So the space of finding the best expert is omega n. Okay, so when you look at this, you might say, okay, maybe there's not much hope for solving the experts problem in the streaming model. You can't identify the best expert. Simple reduction. But this is not the end of the story, right? Why does a low regret algorithm need to find the best expert? Okay, so maybe it doesn't, right? I mean, you could imagine it. There's some simple instance where maybe it's hard to find the best expert, but it follows some expert that's right for many days. And then the expert starts being wrong, and it follows some other expert that's right for many days. That's actually what would happen if you took set disjointness and you copied it. You took Alice's input and you copied it for t over 2 days. So the same outcome on t over 2 days. Took Bob's input, copied it t over 2 days, same outcome on each of those days. You would just follow some expert that's right on those t over 2 days. You'd quickly figure out one and follow it. And then, around the t over 2 day, it'd start messing up and you'd switch to someone else. And, you make a few mistakes in your switch, whatever, you're right on almost all the days. And you never solve set disjointness. Okay. What if, there's a question in the chat box, what if n-1 experts output with probably 1/2, 0, 1, one expert that's always correct? Okay, good. Yeah, so Chen Wang asked this question. Yeah, so we're gonna see a distributional version of set disjointness in our lower bound. So let me get back to that question. We certainly need a distributional version, but we need a little bit more too. Okay, so the moral here is that we don't need to find the best expert. And let me just state our results and then get into some of the details. So the first result is a lower bound, which says that any algorithm that achieves regret delta, bounded away from 1/2 with some constant probability, needs to use n over delta squared t memory. Okay, and this lower bound, it holds for the arbitrary order streaming model, but it's even stronger than that because it holds for a weaker model, the random order model. And in fact, it even holds for an IID stream model, which I won't define, but you can guess what that means. But let me just put this bound in perspective, okay? So, the standard regret that you get in offline algorithms, it's like square root log n over t, okay? Let's forget about log factors. So we think of it as square root 1 over t. You plug in delta as square root 1 over t in this bound, you get n memory. Okay, you can't achieve the standard regret bounds in the streaming model. Okay, fine. But here's a nice potential trade-off. I didn't say that we had an algorithm yet, but as the regret goes to a constant, then you're getting space that's could be as small as n over t. You have a lot of days. This is a significant savings over n space. Maintaining a weight for each expert. You don't have to do that. Okay, so that's a lower bound, and our second result is an algorithm which matches that lower bound, almost. So it's in the random order model, first of all. So the days do need to be, randomly ordered, which makes sense in certain applications. And what we get here is an algorithm that uses, the same quantity, n over delta squared t memory, up to log factors. And it achieves, and delta can be anything, up to the information theoretic limit, up to constant factors. Okay, so you get this smooth trade-off that matches the lower bound that also holds in the random order model. One nice thing about this random order algorithm is the algorithm, the second bullet here. The algorithm is, as I said, almost tight with the given our lower bound, and it's oblivious to the number m. Capital M here, remember, is the number of mistakes of the best expert. Okay, so it doesn't need to know, stuff that you shouldn't assume that you would know in practice. And yeah, as I said, the third bullet here is, it goes all the way down to, the trade-off is the full spectrum, right? It goes all the way down to the information theoretic limit. It generalizes to non-binary costs. So not just if you're wrong or right, but you have some real costs between 0 and rho, and you get a regret which grows as rho delta. Let me not get into that. So this is tight for random order model. For the arbitrary order model, our third result, we don't have tight bounds, but we have non-trivial bounds. So let me say what they are. So if the number m, again, remember this is the number of mistakes of the best expert, is not too large, so is order delta squared t over log squared n. Okay, forget log factors for this talk. So order delta squared t. So if you want constant regret delta, then you can allow the number of mistakes to be a constant fraction of days. And delta is at least, again, information theoretic limit up to logs. Then there's an algorithm that uses n over delta t space. Okay, that works in arbitrary order streams to get this regret delta. That's this first bullet. And let me just emphasize some aspects of this. This algorithm beats the lower bound. So I just said that there's an n over delta squared t lower bound. Delta is a quantity which is much less than 1, right? So how can we get an n over delta t upper bound? Well, again, there's an assumption here that the number m of mistakes of the best expert is, not too large. And so this actually shows, to the hardness of the lower bound is coming when the best expert, can make many mistakes, when this assumption is violated. But yeah, we beat it, n over delta t versus n over delta squared t, if the number of mistakes is not too large. Again, the third bullet is just saying, we get the full spectrum, it goes down to the information theoretic limit. Yeah, so like if delta is, close to square root 1 over t, this would be n over root t memory. Again, with this assumption on m, in that case, when delta is 1 over root t, m is, close to a constant. So, but yeah, another nice thing about this algorithm is it's also oblivious to n. Okay, so you don't need to know hyperparameters. You don't need to know stuff that you shouldn't know. Okay, so those are the three results.
David.
Yeah, question.
Yeah, so can you go back to the, sorry. Yeah, so I think so. Is it true that like your m should be in certain range? Because if m is very large, sorry, yeah, if m makes a lot of mistakes, as in, for example, like it's randomly guessing, and then your regret should be like easy to get a good regret, right? Because you just like whatever you do, like the optimal is going to do some garbage.
Well, okay. I mean, the thing is, the regret can be, significantly sublinear, right? So like, yeah. So like, if there's no, imagine like the best expert is right, like, a half plus delta fraction of days. This is actually our hard instance, right?
Right,
Then you do
right.
have to distinguish that from random guessing, which is you know, a half, right? Because you want regret
I
delta,
see.
right? And so it's still kind of hard, right? I mean, you'll see that this actually comes
I see,
up.
I see, I see. It's a parameter. I see, I see. You don't want constant regret. You want strictly.
I mean, it's a parameter delta. Yeah, yeah.
Sure. Okay. Good.
Any other questions? Okay, cool. Yeah, so it's about halfway through. Let me try to give you some of the details for these results. So we finished part one. Part two, I'll first discuss the lower bound, and then arbitrary order upper bound, then random order upper bound. Okay, so recall the statement of the lower bound that, you know, you get this this trade-off that any algorithm that achieves regret delta with constant probability requires n over delta squared t memory, and it holds you know, for all these different streaming models. You know, essentially because the hard instance is going to be distributional, so it's sort of automatically random order and so on. So here's the way we prove this. It's again from communication complexity, though the problem is, you know, slightly more sophisticated than the standard set disjointness problem. So it's called distributed detection problem. Okay, so this is you know, estimating like properties of distributions where different machines get a sample from the distribution. You know, these types of communication problems arise in those contexts. But you know, what is it here specifically? So we define the epsilon diff-dis problem as follows. You have t players that are each going to hold n bits. Okay, so you should think of the t players. Each player corresponds to a day. And the player is going to have the n predictions, you know, one for each expert on that day. You know, it's kind of weird, right? Like an expert you might think is a player, it's a person. No, no, no. Okay, so the players are the days, and there are t of them, and each one has, you know, the n predictions for that day. And there are two cases that need to be distinguished. I'm going to call the no distribution. Case one is every bit of every player on every day is an IID fair coin toss. Okay, you know, everything is completely random. We're going to try to distinguish that case from case two, a yes instance, where what we do is we choose an expert uniformly at random, or in fact, it could be, but arbitrarily. We choose an expert arbitrarily. Let's call it L, you know, one of n experts. And what's going to happen is across these t days, instead of the Lth expert being an independent coin flip, it's going to be drawn from a Bernoulli distribution with parameter 1/2 plus epsilon. Okay, so it's slightly biased towards being heads. And all the other, you know, it's IID across the days. It's just, you know, it's heads probability is 1/2 plus epsilon. And all the other experts, you know, on all days are just independent coin flips. So, you know, let me just draw the picture here. Okay, so on the left of this middle divide is a no instance. We have 4 players because we have 4 days. And we have 5 experts, okay, a coin for each day. And, you know, these are just totally random coin flips, okay, independent across all of them. On the right of the divide, this yes instance, L is equal to 2 here. So what this means is the second expert is a little bit biased towards being heads. Okay, so in red, I have these 4 outcomes. And yeah, we want to distinguish these 2 cases. Okay, this is the instance that we're looking at. And yeah, so that's the epsilon diff problem. T players each hold n bits and must distinguish between the 2 cases. Now, there's a simple upper bound for this. You know, randomly choose order 1/epsilon squared players times a log factor, and send all bits of those players to each other. And you only need 1/epsilon squared coin tosses to distinguish bias 1/2 plus epsilon versus bias 1/2. Put a log n there to union bound over the n coins. Yeah, you can do that. But it's not great, right? I mean, that's n/epsilon squared total communication. You have 1/epsilon squared days, and n bits are being transmitted from each of those 1/epsilon squared players. Here's a picture of that upper bound, right? So these two red horizontal boxes, I sampled those 2 days, those two players. Again, players are days. And I just exchange all the bits, and maybe that's enough days to notice a bias in the second expert. Okay, simple upper bound. Yeah, okay, so the first bullet here is just the problem again. The second bullet here is the simple protocol I just said. The third bullet is that it has n/epsilon squared communication. And what we show is that n/epsilon squared communication is necessary to solve this problem for randomized protocols. So that, there's no, you don't have 1/epsilon squared days. You have, any number t of days, but the total communication has to be n/epsilon squared. You don't have to sample players. You can use a sketch or whatever you want. There's no way around the n/epsilon squared lower bound. Here's just some facts and intuition about this theorem in the first bullet, that n/epsilon squared communication is necessary. So the fact is, you need 1/epsilon squared coin tosses to distinguish unbiased coin and bias 1/2 plus epsilon. Okay, so yeah, I mean, seems like that's where the 1/epsilon squared should be coming from. And the intuition is kind of like, well, maybe I need to solve all n instances, right? I kind of have like n instances, one for each expert. Now you don't actually have to do that, right? Because you just need to solve the OR of those n instances. But maybe the OR is not much easier than solving all of them, and that turns out to be the case. Yeah, so there's a question of Arvind on yeah, that is related. So like the fact that a coin flip it's harder to distinguish a bias of you need 1/epsilon squared samples to distinguish bias 1/2 versus 1/2 plus epsilon. But if you're distinguishing bias 0 versus epsilon, then you only need 1/epsilon, as Arvind pointed out. And this is related to our fact that the number of mistakes of the best expert is going to be small. Okay, in our upper bounds for arbitrary order streams that get 1/delta dependence on the regret instead of 1/delta squared. Yeah, that's a good intuition. So the right intuition. Okay, so so how do you formally prove this n/epsilon squared lower bound? So I'm just going to sort of like go through it quickly. All the coins are independent of the node distribution, and so you can use standard direct sum theorems, the second bullet, in communication complexity for an OR of n problems. So Bar-Yosef et al. Has a very powerful framework for this. Those sort of direct sums in information complexity came earlier than that by Chakrabarty et al. So what this reduces to, information adds, communication does not. So what you would like to do is, show that, the information cost of solving one of these n instances is omega 1/epsilon squared, and then you can add it up over n of them. You need to, there's sort of an embedding step in this direct sum theorem, because again, you're not solving all n of them necessarily, right? You're just solving an OR. Is one of them biased? And for that, you need to actually show a high information cost under the node distribution, which for us is just uniform on a single coin. And then that will add up and can be plugged in this direct sum framework. So that's the second bullet. And it reduces the problem to, a single coin now. And we need to show 1 over epsilon squared information lower bound to distinguish between a single fair coin and a coin with bias half plus epsilon. The protocol is always correct, but the information is measured under the distribution when the coin is unbiased. You can do this using some min information cost theorems that use so-called strong data processing inequalities, sort of first shown in work of Ducci et al. There's a nice multi-round extension in Garg et al. And extension to a sparse case in work with Braverman et al. So you can show this 1 over epsilon squared lower bound. I'm not going to say more about that. And using this direct sum that I mentioned. Okay, so the first bullet here is just the problem again. The next 2 bullets are the cases, yes, no, and yes. And just by using this framework, you can get an n over epsilon squared communication lower bound. Okay, what do you do with it? Now when I ask what do you do with it, why is distinguishing the no instance from the yes instance equivalent to coming up with a low regret algorithm? Again, there are these issues that maybe you don't have to distinguish no versus yes. As we saw for the simple 2-player set disjointness, you didn't have to find the best expert. That simple 2-player set disjointness is not a lower bound for the expert's problem. It's a lower bound for identifying the expert, which is way harder. So how do we use this? Well, again, okay, so each player in this epsilon diff problem corresponds to a day, as I said. Each bit in this epsilon diff problem on a given day corresponds to the outcome of an expert. And the sort of idea or hope is that this planted expert in the yes case that has this bias of 1/2 plus epsilon, maybe this indicates an expert that's the best expert, that's doing better. It's outputting more ones, right? It's biased. But what is a very simple protocol that can solve this problem without looking at anything? Well, I just predict 1 on every day, right? I mean, I predict 1 on every day. I didn't have to do anything. And I'm pretty good regret because the best expert is, predicting 1/2 plus epsilon at a time. Doesn't work as a lower bound. Right, so the challenge is, here's like this, the usual table, the rows are the days, columns are the experts. Don't even look at these experts, just predict it's always going to be sunny. And the best expert is predicting it's sunny 1/2 plus epsilon at a time. There's your low regret algorithm. So the way we fix this to make this communication problem work is, so the first bullet, we would like to use this online learning with experts algorithm for solving this communication problem, where we'd like to set the epsilon to be order delta, the regret. And the second bullet is saying, this problem is an algorithm with bad guarantees can still luckily have good costs. And so what we're going to do in this third bullet is use a masking argument. Okay, we don't want it to be that just some like bonehead algorithm just always outputs 1 and solves the and has low regret, without doing anything to solve the communication problem. So we use this masking argument where what we're going to do is the player is going to choose a random bit 0 or 1, and it's going to XOR every outcome by that same bit on a day. The bit, this is called the mask, and the masks are independent across the days. And the outcome, instead of being 1, is going to be 1 XORed with the mask. Okay, so here's the picture. Okay, so on the left here was just what we just said when it's you can just always output sunny without doing anything, and maybe you have low regret. Okay, it's the actual outcome. This is what you say. But what we're going to do is the player is going to choose a mask, which is 1 on this first day. And if it's 1, it's going to flip sunny with rainy. It's going to flip rainy with sunny, flip sunny with, rainy, and so on. So it just flips the bit. And so you look at this, and the streaming algorithm that the player is, running this on doesn't know what the mask is. So, so that's how we avoid just having, always outputting 1. I mean, that's not a good thing to do anymore. Like that will be correct with probably at most a half, because the outcome is also flipped by this mask, you see. So, the outcome is going to be, random, to an algorithm that doesn't look at any of the expert outcomes. And it's also, if all the expert outcomes are random, as they are in the no case, then even if it looks at the expert outcomes, it's random. Okay, so this mask, kind of, it avoids this problem of, just always outputting the same answer, always outputting 1. Okay, so, here is the properties you can show of this reduction. So if you're in the no case, so in this first bullet, sorry, this delta is arbitrary. It's not a constant. If that's confusing, sorry about that. For in the no case, if there's no biased coin, then no expert is going to do better than 1/2 plus delta over 3. No expert can do better, just because this is just a turnoff bound and a union bound over days, right? Like there's just all the experts are random coin tosses. The outcome is a random coin toss. You just can't do better no matter what you do. In the second case, if there is a biased coin, well, if your streaming algorithm is finding this best expert, well, then the best expert is doing pretty well. It's in expectation. It's correct on a 1/2 plus delta fraction of the days. If you set epsilon to be delta in that communication problem, and again by concentration, it's going to be correct on 1/2 plus 2 delta over 3 of the days. So there's a gap between these two cases of order theta delta, and an algorithm with regret theta delta can distinguish these two cases. Okay, so so that's the idea behind the reduction. The first bullet is just saying that the online learning algorithm with regret delta can solve this epsilon diff-dis communication problem with that epsilon in that problem being order delta, and so therefore it must use n over delta squared total communication across the days. And what does that mean? Well, that means for an average day, going from one day to the next, it must be that for an average day, there exists a day for which the communication is at least n over delta squared t. And what is the communication in the simulation? I'm just passing the state of the streaming algorithm from one day to the next. So that means that the streaming algorithm uses at least n over delta squared t space. Okay, so so that's the lower bound. I don't have so much time left. Are there any? Maybe I can take questions at the end, or if there are any quick questions, let me know. So let me move on to the upper bounds. Okay, so let's start with some warm-ups. We're going to look at arbitrary order streams first. And if the number m of mistakes of the best expert is sufficiently small, like order delta squared t, as we said, and delta is above the information theoretic limit, roughly speaking, then you can get n over delta t memory with delta regret. And so a natural idea in the streaming model is, well, I can't afford that much memory. I can only do n over delta t memory. What am I going to do? I'm going to take, let's say, the first n over delta t experts, and I'm going to run one of these classic algorithms on them. Maybe some kind of weighted majority algorithm on them. If they start doing poorly, then I'm going to get rid of them. So call this a pool of experts. I'm going to throw away the pool, or maybe throw away experts gradually in that pool and replace them with maybe the next pool of experts, and run a weighted majority algorithm on that next pool. and hopefully at some point, the best expert shows up in my pool. And, if it actually makes no mistakes, it'll stay in my pool forever. And I won't make many mistakes. So, here's, sort of the high level approach. This first block is like a pool of 2 experts, and we're running some weighted majority algorithm on it. And these 2 experts start doing poorly. And so then we switch to the next 2 experts and use them until they start doing poorly. So here's a simple argument in the no mistake regime. If you iteratively pick a pool of the next k experts and just follow their majority vote, then, so you run a simple algorithm, right? You have a pool of k experts and you follow the majority vote. And if someone makes a mistake, then you just delete that expert. Okay. And if you're wrong, then half of the experts that you currently have are wrong. And so the number of errors you're going to have until the pool is obliterated is order log k errors. Okay, this is if the best expert makes no mistakes. Okay, so in the second bullet, you're going to use n over k pools. You want to, with n over k pools, you want to achieve regret delta t. Okay, and so just solving for k says that the pool size k, the number of experts, needs to be roughly n over delta t. There's this log factor because you make log n mistakes with each pool. Okay, if you have n over k pools, each one makes log n mistakes. You set n over k log n equal to delta t, the total number of mistakes. You solve for k, and this is your memory if the best expert makes no mistakes. Okay, fine, but best expert typically makes mistakes. This first bullet is just saying the algorithm is iteratively picking these pools. Take the first k experts, follow majority vote, deleting at least half every time majority is wrong, moving on to the next pool, and so on. And the intuition is in the next 2 bullets, right? So if the number of rounds is small, like you don't end up finding a new, obliterating the pool, you might not ever get to the best expert. But who cares? Because that means if the number of pools you used was small, then you must have done well. You can only make log k mistakes on a pool. So overall, the regret is small if the number of rounds is small. Otherwise, the number of rounds is large enough so that the best expert gets included in your pool. And it makes no mistakes, so you don't delete it. And then you just correct forever at that point. Okay, so you're sort of balancing these 2 properties. This is the no mistake regime again. In the low mistake regime on this slide, it's just a very slight modification, which is very natural idea, which is that change the pool size. Okay, so if the best expert makes capital M mistakes in the second bullet, use a number of pools which is m times larger. And then you have to solve for how many experts you need in each pool. You solve and you get n m over delta t. Okay, now the number of experts in your pool is your memory, right? Because you're running one of these majority algorithms, on those guys. You need to keep them in memory. They're identifiers. But this is too large, right? We don't want memory which scales linearly in the number of mistakes, m. So we have some fixes, natural fixes. The first fix is, well, what if we randomly sample pools of experts instead of iteratively picking pools? Okay, so that's great. Hopefully, we're going to pick the best expert soon. We'll pick a best expert, but the problem is you cannot guarantee the best expert will be retained. Maybe you randomly pick the best expert, but it's sampled at a time where the best expert is doing poorly and it's thrown away, and then you don't get a chance to get the best expert back. And there is also like buildup of errors that happens. The second issue. What that kind of means is, so it's sort of a bad case study here. It's kind of like, so here I have 8 8 sampled experts. These are the rows. Each column is a day, and on the first 2 days, everyone is right, and then half the experts are wrong. I throw them away, but the remaining 4 experts, they did pretty well on the first 4 days, so they have some history, and it takes some time for them to be considered bad, and you need sort of like twice as many days until that half, you throw away half again, and so on. Yeah, so I guess I'm running out of time, so let me skip over the details, but you can fix that. Just the algorithm is in this first bullet. Repeatedly sample a pool of n over delta t experts and output the majority vote of the pool. And what you're going to do is you're going to delete any expert which is pretty inaccurate. So if you keep track of its accuracy, which you can, I mean, it's just a counter. And if it's wrong on more than a delta over log n fraction of days, then you delete that expert. And what you want to, so that's the algorithm, the whole algorithm, okay? And what the analysis shows is if the number of rounds is small, the pools must have done well, so the overall regret is small. And again, if the number of rounds cannot be too large, because at some point, every time you start a new round, you randomly sample, k experts. And so if you have enough rounds, you're going to sample the best expert. Now, yeah, since I'm really out of time, let me just say at a high level what happens. So in the arbitrary order model, the best expert doesn't make many mistakes. And you're only going to get really screwed up if you sample the best expert on a day where it makes many mistakes around that day. Sort of it's in a dense region, because in that case, the accuracy is going to look bad in that dense region, and you're going to throw away that best expert, and then you haven't made any progress. So we use the fact that the number of mistakes is small for arbitrary order streams to just argue you can't have many of these bad days. And so if you have enough rounds, you're going to have enough chances to sample the best expert. We don't get as good of parameters as we do in the random order streaming case. In the random order streaming case, what you can say is, hey, the best expert, on any contiguous block of days, it does pretty well. It does, as well as it's supposed to be doing globally. And we use that property to do better in the random order streaming model. So, let me just skip over the details here. Yeah, I'll just summarize the results in the interest of time. And so here's a summary with all the results. The first result is the lower bound from communication complexity. The second result is the random order streaming result. So all it does, sample a pool of experts of the appropriate size, run one of these multiplicative weights or weighted majority algorithms, and monitor how you're doing. So you can even check, is the expected number of mistakes that the best expert that I have so far doing as well as the theory predicts? If it's not, I can compute that expectation. I see all the outcomes and I see all my, the actual guesses. Regardless of how I use those outcomes in my random choices, I see the actual outcomes. I can deterministically compute the expectation. And if it's horrible, then I know the best expert is not there. Otherwise, it would contradict the low regret theory. So then I can throw away that pool, and then I sample a new pool. And yeah, so that's how that algorithm works. And as I said, you get better guarantees in the random order model just because things locally look like they do globally. So that's these are just the quantitative results in bullets 2 and 3 for the two algorithms again. As I said, there's a natural generalization to costs that are real, and there's some width parameter rho. And there are many questions that this this work leaves open. So so we don't get tight bounds for arbitrary order streams. I don't know if it's the upper or the lower bound. I don't have a conjecture. And you know, as you know, the expert's problem is used in many other problems in optimization and so on. You know, so how general is this framework beyond the expert's problem? You know, what else? You know, maybe some specific applications where multiplicative weights is used. Can we use these same ideas to design algorithms? So let me just stop there, and thanks again for your attention, and to the organizers for inviting me.